Chapter 8, Section 2, Day 1, Estimating a Population Proportion. The learning targets for this lesson are to be able to construct and interpret a confidence interval for a population proportion. Imagine that we had a container full of different colored beads. There's 3,000 in all, and our goal is to estimate the actual proportion of red beads in the container. Here are the steps we would go through to be able to do this. First, determine how we could use a cup to get a simple random sample of beads from the container. This would entail stirring the beads thoroughly before we drew the simple random sample. Next, we would collect a simple random sample of beads. Then determine the point estimator for the unknown population proportion. And then after we've done that, we would find the 90% confidence interval for our parameter P. We must consider that all conditions are met to use this method. Suppose 107 out of 251 beads are red. Our point estimator for P hat would be 0.426. To determine our confidence interval, we first need to check the conditions. As long as n times p and n times 1 minus p are at least 10, our sampling distribution of p hat should be approximately normal. The mean of the sampling distribution p hat, remember, will be p, and the standard deviation of the sampling distribution would be p square root of p times 1 minus p divided by n. The figure is shown at the right for the sampling distribution. In practice, however, we do not know the value of p. If we did, we would not need to construct a confidence interval to find it. In large samples, p hat will be close to p, so we will replace p with p hat when we check our normal condition. For our example, remember, p hat ended up being 0.426. Our first condition that must be met is it needs to be random. Since we took a simple random sample by stirring the beads of 251 from the container, this is met. Checking the normal condition, checking n times p hat and n times 1 minus p hat, you get 107 and 144, which are both greater than or equal to 10. To check independence, 10 times the number in the sample ends up being 2,510 beads. Since I told you there were 3,000 beads in the container, our 10% condition is met as well for independence. Since all three conditions are met, it is safe to construct a confidence interval. To construct a confidence interval, we need three things. First, we need the statistic, p hat, which we already know. Two, we need to find what's called a critical value. And three, we need to know the standard deviation of the statistic. If we knew p, the standard deviation of the sampling distribution would be given by this formula. Since we don't know p, we use p hat instead, and this becomes our formula for calculating the standard deviation of the sample statistic. This value will then be used in the formula where it says standard deviation of the statistic. If the normal conditions are met, we can use our confidence level C to find our critical value. For example, to find a 95% confidence interval, we use a critical value of 2 based on the empirical rule. Using table A or a calculator, we get a more accurate critical value. If we're finding a 95% confidence interval, that means the area under the curve between our two critical values here would be 0.95. If 0.95 of the area under the curve would be between these two values, that would leave 0.05 left over to be in these two tails. If I divide that by 2, that tells me the area under each of the tails would be 0.025. If I use table A at the front of the book, I would note that my critical value Z star is actually 1.96 instead of 2. This is a more accurate measure for a 95% confidence interval and therefore we will use this 1.96 versus the 2. Here's another example of finding a critical value. Let's say I wanted to find the critical value for an 80% confidence interval, assuming the normal conditions are met. If 80% is my critical value, that means 0.8 will be the area under the curve here. With 0.8 being taken out, there would be 0.2 left over, and if I divided that by 2, I would be left with 0.1 for the area under both curves, both tail parts of the curve. If I search table A to find the critical value with an area of 0.1 to its left, I would find that my critical value for an 80% confidence interval would be negative 1.28. However, that is my negative value. I am actually going to use the positive value to be my critical value. Since it's symmetric, a normal distribution is symmetric, the z critical value over here would be the positive 1.28. We always use positive values to be our critical value. We call our critical value z star when we're dealing with proportions, and our confidence interval for proportions can be written as p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. Notice that in the definition for a one sample z interval for population proportions, our three conditions must be met. We must have a simple random sample. The number of successes and failures must be at least 10. That's n times p hat and n times 1 minus p hat must both be greater than or equal to 10. And the population is at least 10 times as large as the sample. So to be able to use this formula, those three conditions must always be met. So back to our example. I wanted to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. I am claiming also that 50% of the beads are red. I want to use my interval that I come up with to comment on this claim. So again, our p hat value was 0.426, and we checked the conditions earlier, so we don't need to go back through that. With a 90% confidence level, the lower tail area under the curve would be 0.05. If I use table A to find my critical value, z star ends up being 1.645. So in constructing my confidence interval, using this formula and substituting in the values I know, we get this. Running this through my calculator gives us from 0.375 to 0.477. So we would then say we are 90% confident that the actual proportion of red beads in the container is between 0.375 and 0.477. Now, coming up with this 90% confidence level or interval, looking back at my claim that there's 50% of the beads, we would conclude that since the interval gives us a range of plausible values for p, and since 0.5 is not contained within the interval, we have reasons to doubt my claim. When doing a confidence interval, there's a useful acronym to help us remember the steps you must go through to complete the confidence interval, and it is called PANIC. In PANIC, the P stands for parameter of interest. You need to state what the parameter you're looking to try to estimate is, and also what confidence level you're going to use. A stands for assumptions and conditions. You need to make sure your conditions are met before calculating the interval, or give a plausible reason why you assume that one of those conditions must be true. N stands for the name of the appropriate inference method or writing out the equation. In our example, that would be p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. This formula will change when we do different kinds of confidence intervals. I stands for calculating the interval. You can only do this if the conditions are met. And C is conclusion and context. You must always interpret your interval in the context of the problem. That's what we did when we said we are 90% confident that the actual proportion of red beads in the container is between 0.375 and 0.477.